Okay, recording is started. All right, hello. Okay, more networking potpourri, very fun. So, like most of the hardcore networking protocols are over with. So the rest of the way we'll just be looking at kind of high-level overviews of stuff that again, like this could probably fill a whole class, but we'll give you some highlights. And then if you're interested, you can always look more into it. Okay, so last time there were two main topics. We talked about denial of service. And the idea was there's a new property in town that we care about called availability. And if we attack availability and make users unable to access the service, that's called a denial of service attack. We talked about how you can attack a service by like crashing the program itself, like a buffer overflow or SQL injection, delete the whole table, or you can overwhelm the limited amount of resources that a computer or a server has. We also talked about how you can attack things at the application level. So here you're attacking the program itself that's running, or you can attack the networking protocol itself, like make TCP break or break, TLS or something. And so both of those are places where you can attack. We talked about specific attacks like DNS amplification. You spoof a little DNS packet, and then the DNS server sends a huge packet to the person you're trying to overwhelm. We talked about distributed DOS, where multiple computers overwhelm a single target. We talked about SYN cookies, or SYN flooding, where someone spams a bunch of SYN packets, causes the server to start up a bunch of connections with all these places where they're allocating memory. And we talked about how SYN cookies is a way to fix that, so that instead of allocating memory instantly when the SYN shows up, they send back the state to the client, and then the client sends the state back at the very end. And only then does the server actually allocate the memory. Okay, so that's the first topic. Second topic was firewalls. And we talked about how if you have all these different computers in one network and you want to secure them all at once, you can build a firewall. And this is a single point of access where all the packets coming in or going out of that network have to pass through the firewall. You can write your own code to define what packets the firewall allows and which ones the firewall does not allow. It could be stateless. It doesn't think about the history of old packets. It could be stateful. It could be really smart and construct back TCP connections and think about what they're saying. You can subvert them, as we saw. And then we briefly talked about proxies, where instead of the firewall looking at every packet one by one, the firewall is a man in the middle. And if you want to talk to someone on the inside, you connect to the firewall first, and then the firewall forwards your message to the inside. Okay, so today's topic, there's just one, is intrusion detection. I find it really cool because there's not a lot of like super technical, you got to see this like 10-step handshake or whatever. It's mostly just high-level overview of things that you'd want to think about on this topic. I find it really nicely organized. So I guess we'll just get into it. Okay. So the motivation for today is that for basically all of this class so far, the framing has always been, here's an attack. How do you stop it? And so, for example, oh, here's a buffer overflow. And if you use a stack canary, you can make it harder for the attacker to perform a buffer overflow. Or like, here's SQL injection. If I escape characters, I make it harder for the attacker. So we've been trying to prevent attacks. But one thing we haven't actually really talked about is, well, most of these defenses, they're not perfect. Okay, there's a couple that are perfect, like don't use C, that's perfect. But most of them are, not perfect. And even if you come up with a good defense, you're not going to stop every single attack. So far, we've only been talking about how to prevent attacks. But one of our security principles said, if you cannot prevent an attack from happening, you should still be able to detect that it happened. So today is all about this like entire second half of security that we haven't talked about yet, which is how do you actually detect the attack when it happens? So maybe your prevention method didn't work. You added the defense, stack canaries or whatever, but the attacker still got around the stack canary. So how do you know that the attack actually happened? That's going to be our goal for today. Okay. So to motivate the intrusion detection ideas that we'll be talking about, we need an attack to detect. I could use buffer overflows or whatever, but I'm going to take this opportunity to show you one more attack just because I can and because it's really common. So it's called a path traversal attack. And by showing you this, by the way, I think we have checked off almost all of these, which is kind of cool. So this one is up there as well. So let's take a look. And again, this is just another attack that's out there. And I'm just going to use it as a way to motivate all the intrusion detection things that we'll be seeing today. Okay. So maybe you're familiar with file paths. If you've like never worked in a terminal, you probably have seen these things. So we know that a file path tells you where a file is. And you can say, well, it's in this folder / this folder / this folder. Other special characters that you might have used before in a terminal. if you've ever used one dot, if you've ever done like dot slash something, dot slash XSplit in project one, what does the dot represent? The dot represents the current directory that your terminal is in. And if you've ever done something like cd dot dot, what does the dot dot mean? That's shorthand for what the parent directory is. So the parent folder that you came from. Okay, here are some examples of what that would look like. So here's a file path. It's a pretty innocuous one. It says start at the slash, which is the root directory, go to the home directory, go to the public directory, go find the evanbot.jpg file. Okay, pretty standard. So you follow the arrows and you're all good. Here's another one where maybe you've already navigated your way into the public directory. So maybe you've opened a terminal in the public directory, you ran cd or something, and you say dot/codebot.jpg. So how does that work? The dot represents here where you are. There's the dot, and then you go to the codebot.jpg file. Okay. And finally, here's one that's kind of weird. So remember that dot dot that takes you to the parent directory? You can also use it inside a file path. So I can say, okay, slash home, that's the top, slash public, go into the public folder, oh, dot dot, so go back up to wherever you came from, and then private, go to the private folder, passwords.txt. It is a very strange file path, but it is valid because this dot dot is just shorthand for go back to where you came from. Okay, so it's valid, it's kind of strange, maybe we'll use it for some attacks. Okay, so the intuition is, let's say there's this like website that's going to give you files. So I have some website out there and I want to let the user request some images. So I'm going to ask the user, hey, what file name do you want? The user says, I want evanbot.jpg. And the backend says, okay, well, I'm going to serve all the files in the public directory. So I'm going to look in the public directory, plug in whatever the user says, which is evanbot.jpg. This forms a file path, and the file path takes me to this file. I will send that file back to the user. So pretty standard. User enters something, we substitute it into the file path, and then we give it to the user. Maybe having seen all those different web attacks where we did SQL injection and XSS, maybe you already see where this is going. Because what if I entered something like this, right? This is kind of part of the file path that I saw earlier. And if I take this red input and I plug it in /home/public/ whatever the user wants, well, we already know from before that this file path is going to say home, public, oh, dot, dot, go back, private, passwords.txt. And suddenly, even though I hard-coded the home/public to try and only serve the folders in the public folder, I have now given the user a way to find the passwords.txt file by inserting that dot, dot, the special characters. Okay, so that's the attack. It's kind of similar to, say, SQL injection, where there's some input in the backend, and you get to substitute in as the attacker your own input. And if you substitute in some stuff like dot dot, it gets treated as part of the file path, and that's not good. Okay, so that maybe lets you authorize files that you're not supposed to access. Often you use the dot dot because that's how you go up a directory. So you can navigate into other directories that you want to find. And we can talk about ways to prevent this. So if this were like any of the previous lectures, we would stop right here and say, well, the way to defend it is make sure that the user input is not treated as a file path. So maybe this dot dot, like escape it somehow, or tell the user you can't have dot dot in your input. So we would say, okay, just don't allow the special characters or escape them, and we're done. Okay, but that's not what today's about. Today's not about preventing, it's about detecting. So maybe we have some defense for this thing, but what if it's not good enough? What if this attack still happens? How do I detect that this happened? That's our goal for today, but that's our motivating example. Okay, is everyone good with path traversal? Now you know what it is, so you can use it on the project or whatever. And also, we'll talk about how you would detect it. Okay, so first we need to decide what kind of detector we want. So here's a couple types that you could consider. Okay, there's 3 right there. Let's talk about them one by one. So the main difference is where you put them. So I guess the first question you can ask yourself is, if I want to be able to detect something, I need to put some machine somewhere that does the detecting. So I need to have some program or some code that's running that can detect that the attack is happening. So the first question is where do I put it? So here's a picture of a network that might seem familiar from last time, right? We have all these computers inside that are all connected up in some local network. If they ever want to talk to the outside world, they have to go through this router, and then the router forwards their message to the outside world. So it's a picture that we've seen over and over again. And so the only question now is that I have a machine that's going to do the detecting. Where should I put it? So there are lots of different choices. So I'm going to first decide to put it here at the router. So there's some machine sitting right here that does the detection. And if I put it there, then it gets a special name. It's called the Network Intrusion Detection System, or NIDS. And why is it called the Network Intrusion Detection System? Because I'm putting it here. And so it's thinking about things kind of at a network layer. I'm going to protect all these computers inside by putting the detection here. Okay. Great. So there it is. I'll put the detector right there. At this point, you might say, this kind of looks like a firewall. I think they do have some things in common. The main difference is that the firewall was actively deciding what to allow and what not to allow, but this is going to only think about detecting things. Okay. So let's take a look at what it would look like. Okay. So one thing you could do then is, because I want to protect all the computers on the inside, I can keep track of all the connections that are ongoing, kind of similar to what the firewall was doing. And then I can look at all the packets flying back and forth and think about like, well, does this packet indicate that an attack is happening? Or does this packet not indicate that an attack is happening? And if the packet somehow seems suspicious, maybe the detection system will start going off and say, uh-oh, there's an attack. You better check something out. So that's the one thing you could do, or how you could build the NIDS. And that's why putting it at the network or at the router works. It's because you can look at all the packets going back and forth and see if you spot anything funny. Okay, so what's good about a NIDS? What's bad about it? One good thing is it's pretty cheap, and we'll see it in contrast to some of the other systems. So we already saw from last time, like it's kind of similar to firewalls. If I install a single network detector at the router, I cover every system in the network because everyone else has to go through me to send packets to the outside world. So I can cover all the systems on the inside with a single detector. That's pretty cheap. It's easy to scale, relatively speaking, because if the network inside gets larger, right, maybe, oh, suddenly the company got bigger and a bunch of other computers showed up, you don't have to go around and like do a bunch of other extra work. You can just take the NIDS and like somehow, you know, make it more powerful. So maybe it's easy to scale if that's your definition of scaling. As we saw with firewalls, which were kind of similar in the sense that you install one thing and secure the whole network. It's easy to manage because there's only one machine that you have to keep track of. You don't even have to tell the end users about this, right? They get the security property of the detector, but they don't have to do any extra work, which is nice for them, perhaps, if that's something you care about. You don't use any of their resources. You just build this one extra detector, and then they don't have to worry about it. It's really good if the system already exists and you don't want to go and like fix all the stuff that's already there or upgrade the stuff that's already there. One thing that's kind of nice is if you remember trusted computing base way back in lecture 1, the trusted computing base here is smaller because the only thing that really has to be security sensitive is the detector itself. Everything else can be insecure. I don't care. Only detector has to be secure for the system to work. Okay. So there's a bunch of good things about it. So why not just use this all the time? Well, the biggest problem with the NIDS is sometimes the thing that the NIDS reads can be different from what the end host reads. And again, we kind of saw this last time when we talked about the packets being rearranged and stuff, but it can get worse. And so here are some more examples of how maybe the NIDS reads the packets one way, but then the person at the end who's actually receiving and processing those packets maybe reads the packets a different way. So they're not speaking the same language. So here's an example where the interpretation might not be consistent. So let's be the NIDS for 1 minute, right? So we are the NIDS and we're right here and we're watching the packets stream back and forth. And we really want to find those path reversal attacks because we don't like them. So we see this packet //etc/password, right? And so we need to think together, like CS161 class NIDS detector. Do we think a path reversal attack is going on? Like, I think so, right? This doesn't look very good. It looks like someone's trying to, navigate up a directory or something. So maybe we should alert. Maybe we should be like, oh, something's going wrong, and warn whoever is monitoring this NIDS. Okay, it's all good. But what if this packet has a TTL that's kind of short? Remember last time, this packet might only have a couple hops left before it just, gets cut off, and maybe it never reaches the end host. So maybe we would make a mistake because we would be here freaking out and being like, oh no, there's a path reversal attack. But if this packet never reaches the end host, then there wasn't actually an attack. So we got it wrong. So this could be a case where we think there's an attack, but there isn't because we interpreted the packet that went through differently. In particular, we thought the packet was going to reach the end host, but it didn't. Okay, so here's a problem where what we see doesn't match what the end host sees. There's another problem, which is sometimes we don't read the packets the same way. So again, we're the NIDS, we see this packet, and we need to think, do we like freak out and tell everyone that there's an attack going on? Or do we just let this packet go and go along with its state? So I look at this and I'm like, well, I don't see the dot dot. Do you? Well, I don't see it. There's no dot dot. So maybe we just let it go and let it go on with its state. But what if the person who receives this packet ends up using URL encoding? So remember URL encoding, sometimes you can have special characters in the URL, and maybe this is part of the URL. Maybe when the person who receives this packet decodes the URL, they're like, oh, what is the 2E? Oh, that's a dot. And this 2E is a dot and the 2F is a slash. Uh-oh, right? Seems like we have a problem. And so if I decode this, maybe I do get a path traversal attack. So we messed up. We thought there wasn't an attack because we looked at this and we were like, oh, there's no dot dot. But it turns out it actually was an attack. So we got it wrong again. And so this time, why did we get it wrong? Well, we got it wrong because we interpreted these things one way, right? We just read them as characters, but the end system was thinking about them in terms of URL encoding. So we weren't smart enough to think about this the same way that the end host is thinking about it. How would you solve this? Well, maybe now the NIDS has to think about URL encoding too. So it's not enough just to look at the characters and find the dot dots. We need to think about what this would hypothetically be if it were a URL. So now it's more work for us to think about that. Maybe we have to speak more languages. Okay, here's one that's even worse. I look at this and I'm like, wait, is this a path traversal attack? Like I see dot dots and I see slashes, but like, what are they trying to access? I see all these dot dots and slashes. Are they even going to find a file that they're not supposed to access? Is this even a harmful input? What is the end host even going to use this for? Are they even going to put this into a file path? Or is this some, I don't know, like someone's playing a game and they type in a bunch of dots and slashes? Like, what is this input, right? It's hard for us to know. And so this is a case where there's not enough information. We see this input and we just don't have the information to judge if this is a path traversal or not. Maybe it is a path traversal attack. Maybe it's not because this never gets fed into a file path. Maybe it is an attack, but it's never actually hitting a file that we care about. Like, I don't know. We don't have the information. So this is a case where it's kind of hard to fix, right? These other cases, oh, maybe I'll fix it by speaking more languages and understanding the encoding. But in this case, like, I just don't know the answer and I have to take a guess. If I guess that it's an attack, I could be wrong. If I guess that there's no attack, I could still be wrong. So there's inconsistency with the way that we think about things as the NIDS and the end host thinks about things. It's kind of a problem, and it's kind of a big problem. So these are all cases where the NIDS just doesn't know. But even worse is that maybe the attacker knows that there's a NIDS in place. And if so, maybe the attacker is going to be really clever. And the attacker is like, oh, I know there's this detector sitting here waiting to detect my attack. So instead of letting the detector find out that there's an attack, they could maybe like maliciously try to fool the detector into thinking there's no attack. So they can take advantage of this imperfect observability or take advantage of the incomplete analysis, all the stuff that we've seen before, and they can try to get around that. And they can take advantage of the fact that the NIDS is thinking differently from the end host, and they can try to come up with inputs that the NIDS just lets go and lets them go through and doesn't detect, but is actually an attack. So they can try to intentionally and maliciously get around the detection, and that would be bad. So here's some examples. We already saw one, by the way, when we saw those time to live packets going through, and we set the time to live packets differently. That could be a case where they were trying to evade detection by the firewall, right? So how do you stop this? Well, it turns out it's kind of tricky, right? And this, again, could be its whole like research field. It's a really deep topic, but at a high level, we have to somehow make sure that the NIDS is thinking the same way as the end host is thinking. But what does it mean to think the same way? You have to think about encodings. You have to think about file paths. You have to understand what this input is being used for. So it can be really difficult to have everyone speak the same language. Another way you could maybe try and mitigate these attacks is you can maybe force the user to have a certain form of the input. So you could say, everyone has to use encodings or not use encodings. So this way I don't have to see this and be like, oh, is this encoded? Is all this like going to decode it? If I force everyone, I tell the users, you have to give me an encoded input or you have to give me an unencoded input, then maybe this way I can detect things easier. I can force everyone to follow the same format. Another option is I could just try all the different options. I could say, is this encoded? Well, maybe it is. I'll analyze it that way. Maybe it's not. I'll analyze it that way too. But as we saw last time, this could be like exponential. There could be so many different interpretations, including ones you don't even know about. One other option is you could just be careful and say, well, I don't know if this is, an attack, but it might be. So I'll just like make a note of it and say, hey, something suspicious happened and check it out later. Okay. So those are all ideas that are out there, but it's a tough problem. Like, how do we actually solve this? It's not totally obvious. And there's another problem that's related, but even harder to solve, which is, do you remember how TLS is end-to-end secure and we were really happy about that? But like, think about the NIDS. Is the NIDS really happy when messages are end-to-end secure? Because now if the NIDS sees a packet over TLS, what does it see? It just sees all the encrypted junk. And it's like, I don't know how to decrypt this. So how do I flag if this is an attack? It's totally encrypted. I can't even read it. How do you expect me to know if this is an attack or not? So again, we have imperfect information. The end host knows how to decrypt it, but the NIDS doesn't. So now the NIDS has a really hard time answering the question of, is this an attack? So how do you solve this? Well, one thing you could do, and like, I kind of feel not super comfortable with this. Maybe you don't either. One thing we could do is we could just voluntarily give our keys to the NIDS so that it can decrypt our traffic. But doesn't that feel kind of weird? Like, we had this end-to-end secure property, and then now we're like giving it up by giving our key to someone else. That's kind of weird. Like, how do we trust the NIDS? Or like, is it okay to give these keys out? So it feels kind of unsavory, right? Maybe you're not a huge fan of it. Maybe you are, but that is one possible solution. Although, the idea of sharing a private key is kind of weird. Okay, so that's the drawback of encrypted traffic. As you can see, there's not like a great solution, but something you'd have to deal with if you're using a NIDS. Okay, that's it for network level intrusion detection. We saw what's good, we saw what's bad, ways to get around it, other stuff you'd like to know. Okay. So that's one option. It's not the only option. So first we put it at the border router and talked about what that would do. Now let's try something different, which is, what if we put the detectors right here? In other words, we install a separate detector on every single computer on the network. If I do this, it gets a special name, host-based intrusion detection, or a HIDS. And so now the only difference is I took the detectors and I put them there instead. Okay, so what happens if I put them there? What are the consequences? Well, what's good about it? And you'll see this is kind of like the opposite of NIDS. So what's great about the host-based detection is, well, all those problems with inconsistencies are totally gone, because who is interpreting the message as the detector? Oh, it's the same person who's reading the message. So if the message was meant for the server, the detector is the server, so they can read the messages the same way. So I no longer have to worry about one person reading a message one way and the other person reading the message the other way, because the detector is the same machine that's trying to read the message. That's great. This is on the end host. I don't have to worry about the time to live thing where the packet doesn't get there, or inconsistent interpretations. I don't have to worry about encryption because I'm on the same machine with the private key. So that's nice. Another kind of nice thing that wasn't mentioned in NIDS is that I can also stop attacks within the network. So if I have a detection system on every machine and there's someone inside the network sending attacks, I would catch that as a HIDS, but the NIDS wouldn't catch that. So that's kind of nice. If you're talking about scaling, there is an argument that HIDS scales better if you think that someone's trying to overwhelm the NIDS. So if we put the NIDS right there, there's the detection system, someone could overwhelm it, right? It's right there, someone could DOS it from there. But if you have all these different machines, it's harder to DOS all of them at once. So maybe that's something you prefer. But again, kind of depends on your definition of scalability. What are some things that are bad? It's basically, again, all the opposite of what the NIDS had. So remember how the NIDS was super cheap? It was one machine to protect everybody. Well, now you have to go around and install one machine and one detector for every single server on the network, including servers that are old, need to be upgraded, servers that you don't even know exist. So it could be really difficult and expensive. And even though it stops most evasion attacks, it might not stop all of them, depending on how this HIDS is set up. So maybe the HIDS doesn't understand the file name parsing, and then it's unable to detect those. So still not perfect, but maybe better. So it's a trade-off, right? There's no right answer to which one you want to use. Maybe use a mix of them. But as you can see, when you want to decide which one to choose, you have to think about the trade-offs. Okay, that's it for HIDS. Anything else you want to know? Okay. So the final system is kind of not in the, like contrast between these two, but it's still really useful. It's called logging. And so here the idea is that, well, a lot of machines out there, I guess I'll just pull up everything. Okay, so a lot of machines out there already generate logs. So for example, if I'm running like a web server or something, maybe the web server is printing out a lot of logs, messages telling you what happened, right? I don't know if anyone's played with web servers before or something, but that's something that happens. Or maybe like you run a script, like a program or something. Like the other day I was editing a lecture or whatever, and I used like, FFmpeg or whatever, and it spit out all this output telling me what it was doing. So you can imagine a lot of tools out there, they spit out messages telling you what's going on, right? And so maybe one thing I can do is if I'm running this service and the service spits out all this message or all these messages telling me what's going on, maybe I can just take those messages and read them, and the messages say, oh, attacker, or user did this, I did this. And maybe I can just read those messages and see if anything is suspicious. So that's the idea behind logging. The systems themselves are already spitting out a bunch of messages, which is a benefit. I don't have to spit out the messages myself. So I can just use the messages that are already being outputted by the service. And then like maybe every night after the service closes or whatever, I can just run a script on those files. It could just be like some Python script that reads the lines one by one and just sees if the file itself has any evidence of attacks. So nothing too fancy here. I just use the logs that someone else has already generated. And then I just run a script on like the text file to see if anything indicating an attack happened. So what's good about this is it's cheap. I don't have to build any logging systems of my own. I just use someone else's system and just run like a Python script every night. Nice and simple. I don't really have to worry too much about ambiguities because the logging system is the end host, right? The person generating the logs is the person processing those messages. So I don't really have to worry about two different people interpreting things differently for the most part. But there is one really big drawback of logging, which is by the time you see that message that's suspicious, right? The log tells you that something has happened, but that thing has already happened. So if you're doing logging, you can't detect attacks in real time. You can only detect after the attack has happened. So you look at the log and the log says, hey, someone just tried to access the passwords file. And you're like, great, I found an attack, I'm going to detect it. But maybe it's too late. Maybe they already have the file. So you can only detect things after the attack happens, unlike the other two, where you can maybe detect things as soon as the packet comes in. Then again, there are some evasion attacks. Maybe if the Python script isn't super smart and it doesn't understand URL encoding, you can still be in trouble. Okay. That's logging. That's the third place you can put something. So you're not really putting something at the end host or putting something on the network. You're just analyzing the log files that get spit out. Okay, cool. Well, one other problem that comes up is if the attacker is super clever, they could change the logs. So we know the logs are being stored somewhere on the computer, like on disk or something. Maybe the attacker, when they're attacking, could also delete the files. And then now there's no evidence of the attack. So you have to be really careful. Okay. That's it for the places where you can put detectors. That's like one part of today down. So next, it's kind of a separate but related topic, which is measuring how good they are. Okay. So we talked about where to put them. Now we have to think about how do you measure if a detector is good or bad? So the way that I think we should measure is thinking about what kind of mistakes can a detector make? So we know that we just keep asking the detector the same question. The only question the detector has to answer is, was there an attack? Yes or no? And the detector, oh, that's kind of harder to say than I thought. The detector can say whether or not there's an attack or not, and the detector can get it wrong in two different ways. And maybe this seems familiar. If it doesn't seem familiar, it's okay. One way that it could get it wrong is the detector like panics and says, oh, there's an attack, but there actually wasn't. So the detector got it wrong, and we call that a false positive. There was no attack, but we said that there was false positive. The opposite is there was an attack, but we were just like, oh, there's nothing wrong, go on with your day. And so that's a false negative because we missed an attack that actually happened. Both of these are errors, but they are different types of errors. One of them says there was no attack and I panicked and said there was an attack. The other one, there was an attack, but I missed it. And so when I want to measure the detector accuracy, it's not enough just to give like one number telling me how good it is. I need to measure both of these because there are different types of errors. So I can measure the false positive rate. I can measure the false negative rate. If you remember your CS70 probability, the way that I measure the false positive rate is I look at all the cases where there's no attacks. So I summon together all the scenarios and situations where there was no attack, and I count how many of those cases there was an alert. That's the false positive rate. So it's only among the cases where there's no attack, I count up the places where I mistakenly panicked, and that's the false positive rate. The opposite of the false negative rate, I collect all the cases where there was an attack, and then I count up how many I missed. That's my false negative rate. Okay, so I should measure these, and I want to keep them as low as possible, right? Like the probability of accidentally alerting should be as low as possible. The probability of missing an attack should be as low as possible. So one question to ask then is, how good can these things get? Can they be perfect? Can I build a false positive rate 0% detector? So what does that mean to have a detector with a false positive rate of 0? a false positive rate of 0 means that when there's no attack, so I sum up all the cases where there's no attack, there is 0% probability that the detector alerts. How do I build a detector that alerts with probability of 0% to get that 0% false positive rate? I could build something like this. So here's a detector. It takes in an input, and what does it do? It doesn't look at the input. It just immediately says, nope, nothing is wrong. So you give it anything, and it says, nope, nothing is wrong. Seems like a pretty silly detector. But what is the false positive rate here? It's 0, because what is the probability that it accidentally flags on a non-attack? 0, because it's never flagging. So this gives you no false positives, but hopefully we all agree that simply always saying there's no attack is probably not very good. What about 0% false negative rate? How can you make sure that you never miss an attack? Right? This is a question that's like almost so silly, it's stupid. How do you never miss an attack? You simply always say there's an attack. So whenever someone gives you an input, you're like, yep, that's an attack. You're never going to miss one. But is that really a useful detector? Probably not. Okay. So this is to say you should not actually use these, but this is to say that when you make a good detector, you need to balance these two. And often there's going to be a trade-off where if you have a better false positive rate, you'll have a worse false negative rate and vice versa. So you have to be really careful and think about which of these two you value more. And it turns out that not only do you have to think about the trade-off between these two, but depending on the thing that you're trying to protect, the trade-off could be different. So here's an example where false positives and false negatives can affect, or like, I guess, the setting itself can affect whether or not you care about false positives and false negatives. So in particular, maybe these two things have different costs. So here's an example. Fire alarms, those are detectors, right? Their job is to detect if there's a fire or if there's not a fire. And so fire alarms can go wrong in two different ways. There can be a false positive or a false negative. And so, well, again, we can't have perfect false positive rate. We can't have perfect false negative rate. We have to think about trade-offs. And in this case, when we think about the trade-off, we should also think about the cost of getting it wrong in either direction. So what is the cost of a false positive with the fire alarm? That means there's no fire, but the alarm goes off. What is the cost? Cost is I have to get up. It's like 3 a.m. The alarm goes off. I'm like, ah, crap, I got to get up, go outside. The fire department has to come, waste some time, check the building and be like, yep, it was a false positive. Everyone go back home, right? So I was annoyed. My sleep was disturbed. The fire alarm or the fire marshal, whatever, had to waste time coming over to check the, the false positive and then tell us there's no alarm. So everyone is kind of annoyed. So there is cost to it, right? It's not good. But then what is the cost of the false negative? What if there's a fire and you miss it? Like there's no more building, right? That I would argue that's worse. And so depending on your priorities, maybe this is a case where you're okay with some false positives if it makes your false negative rate really low. So there is no one detector out there that is the best detector always. It depends on your setting. Maybe there are other settings where you prefer to have more false positives or fewer false positives and more false negatives, then you want a different detector. So it really depends. There is no perfect detector that always works. Okay. And so that's how we see that like the cost can affect whether or not the detector is good or not. So you can have a good detector, but you have to balance the trade-offs, and whether a detector is good can depend on the setting that you're using it in. Okay. This also reminds me, like 3 or 4 semesters ago, there was an exam in like one of our buildings, I think Evans or something, and the freaking fire alarm went off. So that was the case where I thought the false positive was very high because I had to like cancel the exam or whatever, but that's a different story. Okay, ask me about it later if you're curious. But maybe that's a case where the false positive was really annoying. I don't know. Okay. Anyway, this is a situation in general, like, yeah, we had to cancel the exam or whatever, but at least the building is still standing. So maybe that's a case where false negatives are worse. I don't know. Or maybe it's good if Evans, okay, I shouldn't say that. Okay. Anyway, I don't know. Maybe we want a detector with a low false negative rate if we would like Evans to stay standing. I don't know. Aren't they going to like remodel it at some point? I don't know. Okay. Anyway, there's also something else that kind of matters. And so this one requires a little bit more probability to really like hammer down. So I'm not going to like force you to remember this, but this is a case where it's kind of tricky. And the idea is that the rate of attacks also affects the quality of your detector. And it's kind of a paradox and hard to see right away. So I'll try to talk you through it, but it's kind of heavy duty. So the idea is, let's say there's a detector that has a 0.1% false positive rate. That's really good because that means that if you present it 1,000 innocuous inputs that are not attacks, it will only get one wrong. That's pretty good, right? You give it 1,000 things, none of them are attacks, and it messes up just once. Pretty good. Okay, so let's take this detector and use it on two different worlds. So let's take this detector and use it on system number one or scenario number one. In this scenario, there are 1,000 attacks or 1,000 requests that are not attacks, and there are 5 attacks per day. Okay, so what would this detector do? Well, this detector would take the 1,000 non-attacks, and how many would it goof up on? Just one, right? The other 999, it would correctly identify as not attacks. It would mess up on just one. And maybe we get lucky and flag the other 5 attacks. So that means that we got 1 false positive and maybe like 5 other attacks. That is 6 things to check in total. 5 of them are attacks, and we catch them and we're like, great, found the attacks. One of them, we investigate, oh, not an attack. This detector messed up, and we throw it away. That's not so bad. Here's another scenario. Suddenly, our server becomes super popular and tons of users start using it. So now there's like 10 million requests that are not attacks, and there are still 5 attacks per day. I use the exact same detector. I'm not changing the false positive rate. Everything is the same. So now, how many false positives do I expect to see? There are 10 million requests that are not attacks, and for every 1,000, I mess up on 1. So in total, if you do the math, there are 10,000 false positives. I think the math is correct. Let's trust that it's correct. There are 10,000 false positives, right? 0.1% of these 10,000 non-attacks accidentally get flagged. So there's 10,000 false positives. Okay, so why might that be a problem? Well, in the previous case, there were 5 attacks, 1 false positive. So I looked through, 6 things. I found the 5 attacks, and I was good. But what about over here? Now there are 10,000 false positives. Even if I catch all 5 attacks, there's no false negative or something. That's still 10,005 things to look through, and 10,000 of them are false positives. So how useful is that for real? Like, well, now maybe someone has to like manually check 10,000 requests to see which ones are actually attacks, and they have to like pick out the 5 in the 10,005 that are really attacks. That's kind of hard, right? So maybe here's a case where just by changing the scenario, this detector went from being pretty good to not so good. And all that I changed was that there were a lot more non-attacks. So all of this is to say that if your base rate of attacks is really low, it is just really hard to find the attacks, right? This is a case where there are only 5 attacks out of 10 million and 5. So the rate of attacks is really low. And that means that even if you have a really low false positive rate, when you go into this pool of 10 million and 5 things, and you just like scoop up a bunch of stuff, you're going to end up scooping up a bunch of false positives that you then have to like sort through, right? And in this case, there are 10,000 of those false positives and only 5 attacks. So the takeaway that you really have to know, I don't care if you memorize this example, but one thing that's good to know is that if attacks are really unusual and rare, like in scenario number 2, it is really hard to find those attacks, because even if you have a really good false positive rate, like 0.1%, when you go into 10 million things, of which only 5 are what you want, and you just like scoop up a bunch of attacks that you flag, you're going to end up getting a bunch of false positives that you have to like weed out manually. So it can be really hard to build a good detector for scenario number 2. Okay, here's a picture. I'm not sure if I'm a huge fan of it anymore, but if you like to, basically shows that like as the number of requests goes up, the number of false positives goes up proportionally. Okay, it made sense to me at the time, but looking back at it a couple of years later, I don't know. Okay, so here's the place where I have to introduce a bit more like probability to really show why this is such a problem. Okay, so it's called the base rate fallacy, and so again, we're going to assume the same thing from before, which is that there's a 0.1% false positive rate, and every attack gets detected. Really good detector. Like these percents are so low. And if I have this scenario where there are 10 million non-attacks and 5 attacks, how many false positives did I fish out? 10,000 of them. And how many real attacks did I fish out? 5 of them. So I have 10,005 things, right, that are flagged. 10,000 of them are false positives and not really attacks. 5 of them are attacks. So then question for you, see if you remember your CS70, is if you see the detector alert, what is the probability of an actual attack happening? You see the detector alert, it's going off. Is it actually an attack, or is it a false positive? That's your question. There are 10,005 detections, 5 are attacks, the other 10,000 are not. So the probability that this is an attack is really low. That's so weird, right? Somehow I have this really good detector, but when this detector goes off, there's only a 0.05 probability or percent probability that it caught an attack. And that's so weird. That's why people call it the fallacy, because when you see the thing go off, you should really be thinking attack because it's a good detector. But because the base rate is so low, even though this thing goes off, the probability that it is actually an attack is 0.05%, which is really low. And so that's so strange. Even though the detector alerted, it's still really likely that it's a false positive. So it's just really hard to find the 5 true attacks when the base rate is so low. So the fallacy that we're looking at here is that you have this detector, it's really good, it goes off, but unintuitively, when it goes off, with overwhelming probability, it's a false positive. That's so strange. Okay. So that's the fallacy. Again, if you don't have the exact probability, it's okay. But the important thing is that the base rate can affect the quality of detectors. This detector was super good when there were 1,000 legitimate requests. But once that 1,000 became 10 million, suddenly not looking so good. Okay, that was the takeaway. You have to know back to stuff that is not blue background. Okay, so then question is, well, I have all these detectors. Some of them are good, some of them are not. One thing you could try and do is you could try to put them together and make combo detectors. So maybe I have 2 separate detectors. I went to the store. I bought one detector that detects on smoke, one detector that detects on temperature, and I want to use them together. Well, how can I do that? Well, one thing I could do is I could put them in parallel. Like think circuits, if you remember those. So one thing I could do is I could chain them in parallel. And what that really means is that if either detector goes off, then my combination detector goes off and I think there's an attack. So in other words, if I go out to the store and I buy a smoke detector and a temperature detector, I am going to alert if either one goes off. Only one of them has to go off, and I think it's an attack. And this can also chain or extend to like a chain of a lot of detectors. So maybe I go out and I buy 100 detectors. And if any of the 100 go off, I say it's an attack. Okay, so what's that going to do? In general, that's going to generate more alerts because only one of the 100 has to go off for me to alert overall. So overall, I'm probably going to be alerting more often than I just use any one of those detectors because I'm using them all together. So in general, this is not always true, but roughly speaking, this is going to reduce the false negative rate because if there is an attack and I have 100 detectors, like one of them had better catch it, right? So this is probably going to reduce the false negative rate. It is less likely that I miss. In order to miss an attack, all 100 detectors have to be wrong, which is pretty unlikely. However, this is going to increase the false positive because if even one of the 100 accidentally goes off, I'm going to detect. So this could increase the number of false positives that I have to check. The other approach is to go in a series composition. And what this means is that if you have 100 detectors or 2 detectors, you need all the detectors to alert for your overall combination detector to alert. So in this case, if everyone but one person alerts, you don't alert overall. So what's that going to do? That's going to generate fewer alerts in general because you need everybody to agree there's an attack for you to alert. And that's probably going to reduce the amount of false positives because if you just have one detector accidentally go off, you're not going to alert. Even if you have, like 5 detectors accidentally go off out of 100, you're still not going to alert. You're only going to alert if every single detector goes off. But that could increase your false negative rate because if 99 detectors agree that there's an attack and one of them doesn't agree, well, you're not going to detect if you use this series composition. So you might miss attacks this way. Okay. You can also use things that are kind of in between. You don't have to just go full parallel, full series. But this is just to say that usually if you reduce one rate, you increase the other. There's no free lunch. You can't always just reduce both failure rates. And how you combine the detectors is an example of how those rates kind of trade off. Okay, there's not a mathematical proof, but it's kind of a high-level sketch of how those trade-offs exist. Okay, great. That's it for error detection, rates of detection. How do you measure if a detector is good? Is there anything else you want to know about that before we talk about how you detect? Okay, so yeah, I find this lecture pretty cool because it's really organized, right? We went, where do you detect? Where do you put the detector? And we talked about places to put it. And then we talked about how do you know if the detector is good? How do you measure it? And then now our third question is, how do you detect, right? So far, I've just been saying, okay, the detector gets an input and says, yes, there's an attack, or no, there's not an attack. But how does it know that? Like what thinking is it doing? What logic is it going through to know if there's an attack or not? And it turns out there's actually lots of different ways to think about how the detector detects an attack. So that's our next question, which is not what is detecting or where is detecting, but how. That's our next question. Okay, And just like before, there are some different categories, and we'll go through each one. So without further ado, we'll start with the first one. Okay, this one is called signature-based detection. And the idea is if I see something and it looks like an attack I've seen before, I have this list of attacks that I know about. If this matches one of those list of attacks, then I flag. That's it. That's signature-based detection. And so the idea is that you have this like list of common patterns that attacks follow. And if it matches any of those common patterns, you will flag. Okay. Sometimes people call it blacklisting. I believe the term that people prefer to use these days is like deny list, but sometimes you'll see blacklisting in kind of older settings. And so the idea is you have a list of things that you deny, that you don't allow. And if it's on the list, then you say it's not allowed. If it's not on the list, everything else does not get flagged. Okay. So sometimes people call it a deny list, even though it says blacklisting, which is kind of an outdated term, I think, nowadays. And again, this can happen at different network layers. So just like how we can put the detector in all sorts of different places, we can use this strategy at all sorts of different places. So maybe we can read the TCP headers and do this at the TCP layer, at the network layer. We could also do this at the application layer and think about what the HTTP request is and see if the contents of that match an attack. So you have a choice here of where to put this. Okay, here are some examples. So back to our canonical example of how do you detect a path traversal attack? Well, one thing we could do if we're building a deny list of things that we do not like that indicate a path traversal attack, we could think back and we could say, I remember that ... is what people often use to navigate to different directories. Is this all the path traversal attacks out there? Probably not. But is this a common pattern that path traversal attacks have? I think so. So I'm going to add this to my list, and I'm going to say if any request contains ... I'm going to flag. That's the pattern that I think corresponds to the attack. So I'll put it on my deny list. If I see it, I'll flag. Will it be perfect? Probably not. Will there be false positives, false negatives? Probably, but it's a strategy at least. Okay, if you don't like it, we could also talk about buffer overflows. That's something we could detect. So maybe one thing we could do is we could say, well, I know that when I read a buffer overflow, it often contains shellcode. Is that always true? Not really, but is it mostly true? Yeah, probably. So if the buffer overflow usually contains shellcode, then one thing I could do is maybe I'll keep a database of like, these are the kinds of shellcodes that people tend to use. And if I see a request containing shellcode, then I'll flag. So if it's on my list of common shellcodes, then I'll flag. Is it going to be perfect? Probably not. I'll miss some attacks. I'll get some false positives, but maybe it's a strategy that I can use. Now, something funny here is very off topic, but something funny about this is, has anyone run into the issue on project one? It happens like once or twice every semester where they download the project or they try to upload the solution, and then your browser or your antivirus says no because they think you're uploading an attack. I find it very funny. Okay, but that's a false positive because you're uploading your project. Like you did this as a project, but then the browser thinks you're uploading an attack and it doesn't allow it because your project contains shellcode. So I find that funny. That is a false positive. Okay. So what's good about this? What's bad about it? One thing I like about it is it's simple. It took me like 2 minutes to explain. There's a list of stuff you don't allow that's on there, you flag. It's really good at detecting attacks that we know about, because if we know about the attack, we can put it on the list and detect it. And if it's an attack that we studied in the past before, we can have it on the list and think about it. Something really good is that you don't have to build this list yourself. You can share in the community of security people. There are all these libraries out there that have already been put together that show common attacks, and we can share and like all contribute to it. So you don't have to build these lists yourself, which is really nice. These are general purpose lists that everyone can use. There's some drawbacks, which is if there's a brand new attack, good luck finding it, because if you don't know about the attack, it's not going to be on the list of signatures. So you're kind of screwed. Okay. You also might not catch variants. So if someone takes the attack and modifies it just a little bit to avoid the pattern that you're looking for, then maybe you don't catch it. So maybe they take the shellcode that you're looking for and just kind of tweak it by a couple of bytes, and suddenly you can't find it anymore, or you don't flag it anymore. So you have to be careful. The attacker can even do this maliciously. If they know that you're looking for a certain type of shellcode, they can intentionally use a different shellcode or intentionally modify the shellcode to avoid being found. Okay. So you have to be really careful. And just like before, you might have to parse things. So you might have to say, oh, here's this thing, but I have to read it with URL encoding or something. So you have to be careful. You can miss variants. Okay. To generate false positives. Okay. Cool. So that's signature-based detection. Those are some good and bad things about it. I'm going to go on to the next one unless you stop me. Okay. So we can also do specification-based detection. And this one is kind of just the backwards of signature-based. So in signature-based, I had a list of things that are not good. And if it's on the list of things that are not good, I flag. Specification-based is the opposite. Here, I list out all the things that are allowed. So I say, these are all the things that are allowed. And then if it is not on this list, then I flag, right? So I flag everything except the stuff that's on the list. The historical term for this is whitelisting. The more modern accepted term is like allow list, which we saw last time as well, or specification-based detection. And so that's kind of the idea. It's the opposite of signature-based. I have a list of things that's allowed. If it's not on there, I flag. Here are some examples of how you might do that. So maybe for path traversal attacks, I can look at my folder and realize everything in my folder, evanbot, codebot, whatever, those are all file names that only have letters, like A through Z, 0 through 9. So maybe my specification is that all the file names inputted by the user can only have letters and numbers. If you input anything that's not a letter or a number, I deny it and I flag, right? So I can alert and flag if anything contains something that is not a letter or a number. So I'm specifying what's allowed. Everything else, including the ... is not allowed. Okay. What about buffer overflows? How would you do this? Well, this really depends on your setting. So I'll give you one example, but it can be different based on your setting. So maybe you have a program that asks the user how old they are. It's a C program. The user types in a number, and then that's how old they are. So if you ask how old someone is, they should only be typing numbers, correct? They should only be typing digits 0 through 9. If I ask someone how old they are and they start typing like potato, like that's not the answer, right? And so I could say, I'm only going to allow the digits 0 through 9. That's my specification. Anything else that's not in the 0 through 9 is going to be flagged. And so what about like things like shellcode and buffer overflows? Like when we write a buffer overflow, like what does it look like? It's like there's like A's and there's shellcode, there's all these bytes that are not printable, and that's not an age. So if I see that, maybe I can flag it because it's not part of my specification. Okay, what's good about this? Well, it's kind of the opposite of signature-based. So now, if there's an attack you've never seen before, you can still catch it. Because if that attack doesn't conform to the specifications that you wrote, you're going to catch it. So what's really cool about this is you can actually catch attacks even if you've never seen them before. If you're really careful about this, you can have a low false positive rate, like in the example of ages, right? It's pretty hard to accidentally flag an attack. Yeah, I guess it's hard to have a false positive in the case where there's ages because you're specifying everything that's allowed. And so like if it's correctly specifying only things that are allowed, it's pretty hard to show an attack that only uses digits. So maybe you have a low false positive rate, depends on your setting. What are some drawbacks? The biggest drawback is this is not something that's general purpose. Remember in signature-based detection, I have a list of attacks. Those attacks are like always attacks. So it's a list that everyone can share and contribute to. But in this case, that might not be the case because you need to manually specify what's allowed. And it could be different for every program. This program allows ages. This program asks for your name, so you have to specify something different. This program asks for a password with this set of rules. You have to specify something different. So you may have to manually take your time to specify all the things that are allowed. If you miss the specification and you accidentally leave something out, that could be a problem. If you decide to change your program later, you have to go back and change the specification. So this one is kind of time consuming, and that's the trade-off that you have to make. Okay, so 2 down, 2 to go. Okay, the third one, this one is kind of funky, and I'll try to explain it in a way that's not too weird. But basically the idea is that attacks are usually going to look a little bit weird. So what do I mean by weird? Well, I could either specify what's weird like the previous two cases, or I can just try to be fancy and be like, you know how like machine learning and AI is like all the hype these days. So maybe I'm going to use some fancy machine learning algorithm to automatically develop a model of what is normal. So I'll be like, here's a bunch of input. Like think about it really hard, train on the data, right? Give me a model of what's normal. And if you see something that's not normal according to your trained model, tell me it's an issue. So I'm leveraging, machine learning, or I'm leveraging like statistics to figure out this is what I think is usually normal. And if it's not normal, I'll flag. Okay. So it's kind of similar to specification based. I'm still using an allow list, but it's not an explicit list of what's allowed. It's a model that someone else learned based on what's allowed. Okay. It's kind of weird. So I'll try to formulate some examples, but really it's kind of an open-ended question. So maybe you analyze a bunch of inputs, right? Maybe you don't have to do it yourself. Maybe you outsource it to like some machine learning algorithm. And maybe the machine learning algorithm studies like, oh, this is an attack, this is not, this is an attack, this one isn't. And it studies really hard and it starts to see a pattern, maybe automatically without you having to specify. Maybe the machine learning algorithm is really smart and it realizes when I see the ... it is high probability that this is an attack. So maybe it learns, oh, the ... is part of an attack. So maybe it's going to alert if that ... appears. And so that's not something you specify, but it's something that the machine learning algorithm learns through data and patterns and training data. Okay, what about buffer overflows? And again, this is a rough idea, right? Like how machine learning algorithms work is totally out of scope for this class, but maybe I pass on a lot of examples to the algorithm and it starts to learn something. It sees a pattern and it sees, well, all the things that are not attacks, they tend to be things that a user can type on a keyboard, because that's what most users tend to type, stuff on their keyboard. But attacks, they tend to have things that are not printable, like those raw bytes \XFF. That's not a keyboard character, that's a raw byte that corresponds to some non-printable character. So maybe your machine learning algorithm learns this from data without you telling it. And maybe the machine learning algorithm is smart and figures out, oh, actually, if I see this FF character, I should flag because it's pretty unusual. Okay, so shellcode might have those like FFs and non-printable characters. And if those are correlated very strongly with attacks, maybe the detector can use statistics to learn this and then alert. Okay, so what are the trade-offs? What are the benefits, drawbacks? Again, I can detect attacks I haven't seen before. As long as the attack falls outside of my model of normal, I can detect it. What are some drawbacks? This one's kind of weird, which is if your model is bad, you can actually fail to detect attacks that you know about. Right? As a human, you can be like, I know this is an attack, but if my model isn't smart enough to find it, my model could actually let that attack through. That's kind of scary. I can fail to detect new attacks if they don't look weird enough to the model. What if our model is inaccurate? Like I give the model bad data and it learns patterns that it should not be learning. That could be a problem. False positive rate could be high because maybe there are attacks out there that look unusual, or there are non-attacks that are just simply unusual. Like maybe someone's just a weirdo. They love to type non-printable characters. You would flag them, but it's not an attack. And that could be an issue with your model, depending on how you build it. So it's really tricky. There's kind of a trade-off of, if you only look for super unusual things, then maybe you reduce the false positive rate because you're only looking at the weirdest things ever, but you might start missing stuff because there could be slightly weird things that are attacks. By contrast, if you try to swap it around and say, oh, I'm going to detect everything that's even slightly weird, then you could have a lot of false positives, even if you miss fewer attacks and lower your false negative rate. Okay, in practice, this is not something that most people use. There are a lot of papers about it. If you're looking for like a research topic, this might be a good one. I can't profess to know much about it, but maybe some other people working in the field do. But in practice, as far as I know, this is not super widely used because it's really fickle and hard to get right. Okay, but it's out there and do know that it exists. Okay. Final one is behavioral detection. This one is kind of its own category. And so might as well talk about it. So here the idea is we're going to totally switch gears and say, we're not going to look at the input itself. So far, what have we been doing? We've been saying, here's the input, .. / whatever, or here's the input. This is what the user typed as their age. Is it an attack, yes or no? Behavioral detection is going to switch it up and say, I'm not going to look at the input at all. What the user inputs, I don't care. Instead, I'm going to look at what the input does as an effect, or like what actions happen as the effect of the input. I realize I said that very weird. Okay, we're not looking at the input itself. We are looking at what the input causes the server to do. So we're looking at the behavior caused by the input instead of the input itself. Okay, and it turns out that within this behavioral category, you can even have subcategories, because what do you do with the behaviors? You could do something signature-based where you're like, this is the list of behavior that's not allowed. If it's on this list, flag. You could also do an allow list and say, this is the list of stuff that is allowed as behavior. This is behavior that's good. If it's not on the list of good behavior, then you detect. You could even learn a model if you wanted to, right? So that's behavioral. It has all these different subcategories. But the idea is that you're looking for evidence of attacks. So you do not look at what the user inputs as a string and be like, is this string good or not? Instead, you look at what's actually happening as a result. For example, maybe you look at the file system and you say, hey, what files are you fetching from disk? And if you ever see, wait a minute, why is the program trying to read the passwords file when it never has to? That could be evidence of the behavior being bad, right? What about buffer overflows? Well, maybe I write a program and my program never calls the exec function. I wrote the program, I never called the exec function, and I run it and I watch it and it starts to run the exec function. I'm like, wait a minute, that's not the correct behavior. I was never expecting the exec function to execute. Now it's running that function. That's super weird. I'm going to flag that. And I didn't flag that based on what the user inputted. I have no idea what the user inputted. But if the user inputted something and it caused a function to execute that I wasn't expecting, that could be evidence of an attack. Okay, what's good about it, just like before, it can detect new attacks because you just have to watch the behavior. And if the behavior is bad, there's an issue. In certain cases, there's a low false positive rate. For example, in the example of exec, well, that could be a case with almost zero false positive, because if exec is executing, that's a really, really strong signal that something is really bad that's going on. This could be cheap depending on your system, because behavioral monitoring is sometimes already built into your system. For example, your operating system is already keeping track of files that you're reading, so you could just kind of piggyback off that and use that to help you out. What are some drawbacks? Well, there could still be false positives. For example, in the passwords file example, maybe someone is really trying to access the passwords file legitimately because they want to like log someone in or something. So that could be a case where you have to worry about false positives. You might only detect attacks after they've already happened. So it's kind of like the logging example where you might not see the attack until you see, oh, the exec function is executing. There's probably an attack, but maybe it's too late because the function's already running. So you might not be able to detect attacks ahead of time. Like by contrast to maybe say, if you're doing signature based, you can look at the input. You're like, oh, input's got shellcode. Attack's about to happen. Start to stop it. But in this case, you have to wait until the exec function is executing. And by then, it could be too late depending on your setting. This only detects successful attacks. So if you have an attack that fails, maybe nothing out of the ordinary happens because the attack failed and you might miss it. Maybe you want to know if an attack failed. So it depends on what you're trying to look for. Okay. And again, attackers can get around this the same way they can get around all the other things by trying to avoid some behavior that's malicious. Okay. Cool. So those are the 4 strategies. Is there anything else you want to know before I clean up and talk about some other miscellaneous topics in the field? Okay, cool. So those are the 4 strategies you have to know, what's good about them, what's bad about them. Okay, so in the last, 17, 18 minutes, I'm just going to talk about some other things in the space of intrusion detection that didn't really fit into the rest of the lecture, but I find pretty interesting anyway. Okay, so here's an idea, which is, well, it's not really detecting attacks in real time, but maybe one thing you could do, and again, this just didn't really fit anywhere else, so I'm putting it here. And so the idea is, what if you launch attacks on your own system in order to see what you're vulnerable against and what you aren't? So this is called vulnerability scanning. And the idea is that before you launch your system to the world and give attackers a chance to try and break your system, you're going to try to break your own system by maybe using a tool that like hits it with some common attacks, or by designing attacks yourself, or by paying other people to try and find attacks. And if you find any attacks while you're in the planning stage, you can shut it down right there and fix it before you give it to the world. So this is you preemptively checking for attacks before giving your system out to the world and putting it in production. So it's very widely used. It's not an intrusion detection system necessarily, because that's being used when your system is in production, but this is something you can use to prepare your system for potential attacks, and it works really well together with intrusion detection systems. So something to watch out for if you ever go into this area. Okay, what's good about it? It can be really accurate if you have a tool that tries a lot of common attacks that you know ahead of time that those attacks have been defended against, which is really good. This is good because it's proactive. You are not waiting for other people to break your system before you fix it. You're breaking your own system to check if it's good and really stress test it for security before you ever give it to the world. So it's proactive. That can be really good if you're security conscious. It can be really intelligent because there's something you could do maybe depending on your setting, which is maybe your intrusion detection system isn't perfect and it alerts on something, but you already know you fixed it. So it's probably a false positive. So you can maybe use that to reason about intrusion detection system alerts. What are some bad things? Well, the obvious bad thing is it takes work. You got to do it. You got to go and like make the attacks happen and try to defend against them. So it can take work. I'd argue the work is worth it, but depending on your system, maybe not. If you can't modify the system, this is kind of pointless. So it depends on your system. This could be dangerous. So maybe if your system is really fragile, you have to be really careful, because if you run this thing, what's it going to do? It's going to try a bunch of attacks on your system. And what if you try a bunch of attacks and then you suddenly like accidentally break your system and you can't bring it back? That could be bad. So you have to be really careful about this, run it in the sandbox or something. But that's vulnerability scanning, kind of a cool strategy. Okay. Here's one that I find really cool. So it's called honeypots. Maybe you've heard it before, and maybe it'll sound familiar. So the idea is I'm going to have maybe this big complicated system with a lot of stuff that's sensitive. And inside the system, I am going to intentionally, on purpose, put a system that has no purpose, but is just sitting there. Why would I do that? Because if the system is sacrificial and has no purpose, then nobody should ever be touching it. It doesn't do anything useful. It is just sitting there, right? And so that means that no one should ever be accessing this. So if someone does access it, what does it mean? Maybe they're an attacker who doesn't know what's going on. And they try to access the system, and then we caught them. We're like, you're an attacker because you're trying to access the system that is totally pointless. Okay, so is it perfect? No, there can be false positives because maybe someone just stumbles around and they're not an attacker, but they accidentally touch the honeypot and they could get flagged when they maybe didn't want to be flagged or shouldn't be flagged. So it could be a false positive. And if this sounds familiar, that's because we've already seen a honeypot. One could argue that the stack canary is a honeypot. Why is that? Because the stack canary is a system with no real purpose. That value on the stack, we're not putting it there because it has useful computational value. It is simply there because no one's ever supposed to touch it. So if someone touches it, they're probably the attacker. And that could also have false positives. Someone could accidentally overwrite the canary, but in general, the false positive rate is low. If someone touches the stack canary, you can be pretty confident that an attack has happened, and you can detect it. You can panic and be like, oh, there's an attack, and try to recover by crashing the program or something. Okay, here's some examples in real life that I find pretty cool. So there's an example from hospitals, which basically says, as like an employee of a hospital, it's really important that you do not read records of patients that are not yours. Or so I'm told. I'm no hospital expert, but it seems reasonable that you should not be reading about the medical history of other people that you're not working for. So one thing you could do if you really want to catch people who are, evil and trying to like read the records of other people they're not responsible for, you could pick someone with like a really, you could pick a celebrity who's like in the news and like, super spicy. This changes every semester. Like are there any celebrities who are like embroiled in drama right now? I can't think of any. I'm not up with the gossip. No takers. I think it was Elon like a semester ago. Is it still Elon? I don't know. Okay, so I don't know. You put like Elon Musk's name in the records, and then someone's like, oh, I want to see Elon's medical history. So they open it up, and then when they open it up, we catch them. So that's maybe one thing you could do. I don't know. Okay, maybe it works better when we have like celebrities embroiled in drama, but I can't think of any right now, so we'll have to go with Elon. Okay, other examples are, one thing you could do is you might want to make the honeypot tempting to people, right? Like if the honeypot does nothing, maybe the attacker has no incentive to go after it. But one thing you could do is you could just leave a little bit of money in there. So that's kind of a sneaky little trick, which is, well, maybe on that computer, the honeypot that does nothing, but is just sitting there, you just leave a little bit of free money in, right? Just like a little bit of bait, some free money, some free Bitcoin. And so when the attacker goes into your system, if they don't know any better, what are they going to do? They're going to go into the system. Maybe they don't know what they're doing or what the system looks like. And they look around and they're like, oh, it's free money. Why not take the free money? And they take it. But as soon as they take it, they're an attacker because they've touched your honeypot and no one legitimate should really be touching it. So that could be something worth looking out for. Here's an example of a honeypot that's really powerful, which is if you ever wonder, like, how do they catch spam? Like, how are they so good at catching spam? There's all sorts of different things out there. I don't know exactly how either, but here's an example of a way to catch spam with really good probability, which is you create an email address. You don't use it for anything legitimate. So nobody is supposed to send you real emails, but you take this email address, you post it everywhere, and guess what you're going to get? You're going to get tons of spam because you posted your email address everywhere. And so if someone sends you an email, it's got to be spam because this email is not used for anything legitimate. It's just a total junk email that is only there to catch spam. So that could be a way to trap people. You can think of it as a honeypot because this email is not being used for anything legitimate. So if someone sends this address an email, probably a spam email, and you can catch that and prevent it in the future. Okay, this is pretty cool. I find that one cool. What's good about it? Again, you can detect attacks you haven't seen before. One thing I find really cool is that once you have the attacker detected, when they like access your honeypot, you can start tracking them too, because you can watch, what are they doing? Like, who are they? What are they trying to do? What are their goals? So something you can do that's really powerful is if you find them using the honeypot and they're still working in your system, you can find them and track them down and see who they are and do a bit of like counterintelligence. That's kind of sneaky. Something else you can do is you can distract them. So maybe you have some super sensitive system that's top secret. So you put a little bit of Bitcoin somewhere else and hope that they just go for the Bitcoin and they don't touch your super sensitive system if they don't know any better. What are some drawbacks? It can be tricky to like convince the attacker to actually go get that money. Maybe the attacker knows that there's some sensitive system and they go straight for that and they avoid your honeypot entirely. So they don't fall into your trap. Your bait's not good enough, right? That could be something that could happen. Maybe you have to make it convincing, right? Maybe the honeypot is super obvious that it's not doing anything. No one's going to touch it. Maybe that's less of an issue if you're trying to do something like the spam trap. In that case, the spam is so automated that maybe you don't care and you're just going to like leave it out there and just catch the easy spam that comes to your spam trap. So again, depends on your system and the attackers you're trying to catch and your threat model, but those are some trade-offs of honeypots. Okay, I find it really cool, really sneaky. Is there anything else you want to know? Okay. Okay, more topics that could be their own lecture, but instead they're going to be one slide or half a slide. So one thing that, again, has to happen that we really haven't talked about, we spent a lot of time talking about detection and how you find the attack, not necessarily preventing it. But something else that really has to happen is, like, for better or worse, attacks happen, right? Like, it would be really nice if there was a world with no attacks, but inevitably they're going to happen. And when they happen, you have to be able to recover. And so that's a whole field of computer science, which is how do you recover from attacks and things going wrong? So things you might have to do are, you might have to do forensics, which is a fancy way of saying you have to do detective work. If an attack happens, you have to figure out what actually happened. You have to do a bit of debriefing. Like, what happened? Why was I attacked? How do I make sure I don't get attacked again? What do I have to fix? So you have to do a bit of detective work to try and learn what happened and recover from it. You might have to recover and say, oh, I lost all this data. How do I get it back? Did I have backups that I saved? If something broke, how do I fix it? How do I patch the issues that caused the attack so they don't happen again? That's a whole field that we have to worry about, and it differs depending on the systems that you're building. Okay. What would you need for forensics? You might have to leave logs so that you can figure out what happened. There are some tools out there to help you read the logs to see what happened. But overall, like, really interesting field, but unfortunately not one we have lots of time for in this class. But it's out there, and be aware that it exists. Okay. So one other thing is, at this point, sometimes it's pretty tempting to think, okay, well, I just saw this whole lecture on detection, and I don't see why it's so different from prevention. It seems to me like if I detect something, I should just stop it at the same time. And you'd be right, because all these strategies that we've been thinking about for detection oftentimes will also work for prevention. So we spent this whole lecture, I kind of tricked you into saying, oh, we're doing nothing but detection, but it turns out all of these ideas can also be used for preventing attacks as well. So sometimes you can take detection and prevention and merge them back together and get something called the intrusion prevention system. And so here, not only are you detecting attacks, but you're also preventing them at the same time. So that's pretty cool. Sometimes this is not possible. So for some strategies that we saw, like logging, you cannot prevent because by the time you read the logs, the attack has already happened. So there's no live prevention. Sometimes it's difficult depending on the system that you're building, because if you want to be able to prevent, you have to take proactive action. Like you have to drop a packet or tell someone that an attack is happening or somehow interfere to cause the attack to stop. So it can be kind of tricky. And so for some intrusion detection systems like the on-path NIDs, if it's only passively reading traffic, there's no way for it to detect and also stop the attack. We can find that the attack happened, we can alert, but maybe the on-path NIDs doesn't have the power to stop the attack. But it depends on the capabilities that you give your system. Okay. So it's tricky. How do you stop the attacks? You can use like reset packets. You can change the firewall rules to stop packets from coming in. So kind of a tricky problem. Okay. Something else kind of tricky is that maybe the false positives are expensive now, because think about a false positive in the detection system. In the detection system, if I have a false positive, what happens? You panic and you say, oh, there's an attack. Someone please look at it. Maybe they look at it. There's no attack. Okay, you wasted some manager's time looking at the attack or some IT guy's time looking at the attack. But what about the intrusion prevention system? Because now, not only are you detecting the attack, but you're also shutting it down at the same time. So if you mess up and you make a mistake and you accidentally shut down something that you thought was an attack but wasn't, you could actually affect users who are not out there for an attack or who are not attackers. So maybe, I don't know, like this project one thing where you try to like upload your submission to Gradescope and your browser rejects it because it thinks you're trying to upload malicious shellcode. Well, if your browser prevents you from doing that, that could be an expensive false positive because now you can't submit your project. They've stopped a non-attacker from uploading their code to Gradescope. So that could be a problem. Again, you have to worry about false negative, false positive. This is kind of like a joke slide, so don't worry about it. But it's like, oh, how do you have a false negative rate of 0? Well, you just have the wire with no security whatsoever, right? How do you have a false positive? These might be backwards, I don't know. But how do you have, a perfect detector? You could just have a wire that does nothing. This is basically saying there's never an attack. How do you prevent all attacks? You just cut the wire. Now there's no attacks ever, so stuff like that. Okay, but there are trade-offs, right? You cannot just cut the wire and be like, oh, no attacks. Yeah, but you just stopped everyone from sending their messages. Okay, how do you attack these systems, right? Because the intrusion detection system is a system itself. It's also a computer or a program running code. So you have to worry about the system itself being attacked. So someone could try to DOS the system by sending it a bunch of attacks or non-attacks or whatever. And now it has to analyze every single one. And the detection system itself could run out of memory or space or time. That could be a problem. So maybe the attacker just sends a lot of stuff. Suddenly the detection system goes down and doesn't know what's an attack or what's not. And maybe that's a way for the attacker to get their attacks through, right? Because it's confusing or overwhelming the intrusion detection system. So you have to be really tricky. You could even attack the system itself. Maybe the detection system itself is vulnerable to like buffer overflows or something. In particular, the detection system could be vulnerable to code injection. And why is that? Because maybe the intrusion detection system sees a piece of code and needs to know, is this code malicious? How does it know? Maybe it has to run the code. And what happens if it runs the code? Oh, just got attacked. So it has to be really careful and run that thing in a sandbox and make sure that if it tries to run some test code that's not trustworthy, that it doesn't affect the intrusion detection system itself. Okay, here's an example of a modern intrusion detection system. There are lots of examples out there. I'm not going to talk through it in too much detail, but here we can see that there's some packet filter. So it's like a NIDS type thing. You can, parallelize it. So if you ever need more processing power, you can just stack on some more CPUs or GPUs or whatever to give it some more processing power. That's a good way to, scale it. You can have logging. You can have signature-based detection. So I don't know. I've never used this NIDS before, but if you're curious, that's what it looks like. Okay, we'll get some more stuff. Okay, could also use a HID, install it on every device, but I'm not going to talk through it. Okay, so I have 3 minutes. Here's a kind of long-winded summary because today was a long-winded, all sorts of different topics overview lecture. Hope you enjoyed it. So summary is, there are path reversal attacks. That was our motivating example for the day. You do have to know this attack. It's useful for project 3. And remember, the attack is that if you use the ... it allows you to navigate to higher directories and might allow you to navigate to files that you were not supposed to access. The way that you would stop it and prevent it is to make sure that user input is not treated as a file path. But in general, we were not concerned in this lecture about preventing, but about detecting. So different ways you can classify detectors. You can ask the question, where do you put it? And so if you put it at the network level, it's a network system or a NIDS. And in that case, it's cheap because it's one system for everybody, easy to scale, easy to manage. But the problem is there's that inconsistent interpretation. The NIDS might read something one way, and then the end host reads it a different way. By contrast, you could have a HIDS, which is installed on every single end host. This is expensive because you have to find every single end host and install something, but you solve the inconsistency problems. And it also works on encrypted traffic, which is nice. What about logging? Logging was the idea that servers already generate logs by default a lot of the time. So you can take those text files, run it through a program, and see if any of the logs are evidence of an attack. But the key problem here is that it only detects attacks after they occur. Okay, detection accuracy. We talked about how you would measure if a detector is accurate. And we said there are 2 errors that can happen. If there is an attack and you miss it, that's a false negative. If there's no attack and you flag, that's a false positive. Both false positive rate and false negative rate matter, and trading off between the 2 of them is a really tricky thing. Oftentimes, if you combine detectors, for example, you end up getting fewer false negatives, but more false positives or vice versa. So there's a trade-off. And crucially, there's no such thing as a good detector for all purposes. The quality of a detector depends on where you're using it. How much does a false positive cost? How much does a false negative cost? Do you destroy Evans Hall? And how bad is that? What is the rate of attacks? we saw that if attacks are really rare and hard to come by, then the detector itself can be really hard to design because you can scoop up tons of false positives to come with the actual attacks that you find. And then you have to pick out the attacks within the false positives, and that can be really tricky. Final thing we talked about really quickly is the 4 ways you can detect something. So signature base says, here's a list of things that's not allowed, flag if it's on that list. Specification base says, here's a list of things that's allowed, flag if it's not on that list. Anomaly base says, use some fancy machine learning, get a model of what's normal, flag if it's not normal. Behavioral says, don't look at the input at all. Look at what the input does and see if it's evidence of compromise. And then finally, there were all these other side topics that we just kind of briefly skimmed the surface of. And if you're interested, there's a whole world out there to explore. But that's all right. That's all we have for today. So guess I'll see you next time. There is a lecture on Monday. I know it's the day before Thanksgiving. So if you don't come, I won't be too sad. But I'll be here talking about some stuff. Until then, I'll see you then. Yeah, I guess that's it. Okay, bye.